Hello and welcome to Chemical Interactions for Year 8. This is Mrs. Castanera and we are doing Lesson 5, What are the properties of water molecules? So Lesson 5, Properties of Water. Today the keywords are covalent bond, which we should already know what that is, share, as in the sharing of electrons, molecule, intermolecular, as in intermolecular forces, weak, strong, and dissolve. So first off, I would like you to complete the knowledge check questions, please. You'll need to pause the video to do this. So the chemical formula for water is H2O, and the 2 must be small at the bottom. The charge on the nucleus of an atom, so the nucleus of an atom is positive, and that is because it contains protons, which are positively charged, and neutrons, which do not have a charge. Opposite poles attract. Why is water a polar molecule? Well, as we learnt last lesson, it's a polar molecule because it has a positive and a negative end to it. The positive end is caused by the hydrogen nuclei, and the negative end is caused by the electrons in the oxygen. How do similar poles interact? Similar poles repel. Name the bond between the hydrogen and oxygen atoms. So when the hydrogen and oxygen atoms in water are bonded together, this is a covalent bond. And we know that because it's between two non-metals. Hydrogen and oxygen are both non-metals. Name the force between the water molecules. So each individual water molecule has intermolecular forces between it. Water molecules attracted to each other is called cohesion. So today we will be describing the properties of the water molecule. So water, also known as H2O. So water is a polar molecule and can therefore be attracted to each other. And that's called cohesion, as we learnt last lesson. It can also be attracted to other molecules that have either a positive or negative charge, and this is adhesion. This unique property of the water molecule allows water as a substance to do some amazing things. And we're going to demonstrate some of these things today. So as we know, the cohesive property of the water molecule causes the molecules to stick to each other. Okay, and that's cohesion, the cohesive property. So I'm going to attempt to show you some of these properties. We're now going to look at water droplets as they run down the surface of vertical glass. And what you can't see is that there is water. Well, there is a pane of glass in front of you. Now you'll be able to see it a bit clearer. So I have a pane of glass with water. The more water I spray, the more the droplets will come together, and we'll see what happens to those droplets. Okay, so the droplets begin to come together and they turn into water, the same way that water runs down the shower, for instance, on a morning. You can see that the water becomes larger and larger drops as it cohedes to itself. And eventually those drops become too much, too big, and their weight is so great that gravity takes over and drags them down the glass. There we go, there's that big drop turning now under the force of gravity into a bigger drop that's going to slide. So my next experiment is investigating surface tension using tweezers to balance a horizontal needle on a water within a petri dish. Now I don't have a petri dish. What I do have is one of these little ramekins from one of these supermarket desserts we had. And I'm just going to pour some water in. This is literally water that came out my kitchen sink. So now that I've put the water in the jar, I have two needles. One quite a thick gauge needle, quite big, quite heavy, has a substantial amount of weight compared to this slimmer, thinner, lighter needle. Now on the surface of this water is something called a meniscus, and that is caused by the attractive forces between the individual water molecules, the cohesion between them, the cohesive forces. So if I put this thick, heavy gauge needle and try and balance it on the water, it will just fall straight to the bottom. Its weight is so great that it overcomes those cohesive forces. If I do the same again with the thinner, smaller, lighter needle, the important part here is that its weight is lower, I should, there we go, be able to balance that on the water. And the way you know it's balanced is because if you gently blow across the surface of the water, the needle will move around. So if I were to stir the water, as long as I don't touch the needle too much, there we go, I can make that needle move around freely on the surface of the water. This is what happens with small creatures that can walk on water, such as pond skaters. So that water forms its strong barrier on the surface due to the cohesive forces between the individual molecules, because water is a polar molecule and water molecules are attracted to each other. The last experiment is to see how much water we can drop onto a 2p coin, and this demonstrates the meniscus effect. So I don't have a pipette, so I'm going to use a tried and tested method of physics, which is to get a jug and use a straw, put the straw in the water, thumb over the top to create an air gap, and then there is water in my straw, which you can see. So I'll use this method to pour the water onto the 2p. Now I've chosen too big a straw, but what you can probably see here, and I'll zoom in to make it clearer. What you can probably see there is it looks like a little bubble on top of the 2p piece. The water is not spread out, it is not moving around, it has used that cohesive force between the individual water molecules, so they are sticking to each other to create the bubble effect, so this strong barrier on the outside of the water. And I can put a straw in it and it'll break through that barrier, but the barrier is reformed around it. And I'm going to continue to add water to my 2p piece in the same way, using a slightly slimmer straw, to see how much we can actually get onto this 2p piece. Oh, okay, so as you saw there, it very quickly and suddenly slid off the 2p all at once. So that sliding of the water was again caused by the cohesive forces between the individual water molecules, collectively moving the entire drop of water off of the 2p piece. So we're going to repeat that experiment, this time from the side, so you can see the meniscus more clearly. Okay, so as you can see, I put too much water on too quickly and it went straight off. Let's try that again. So you can see how the water is bubbling, well, it's not bubbling up, it's doming up into a giant sort of bubble shape. And this curve is the meniscus. Wow, that's looking quite impressive there. So you can really see the true effect of that meniscus there, and it's bubbled up and domed that 2p piece really effectively. Now, see how much poking and prodding it can deal with. So you can see as I put this straw onto the dome, it's almost elastic. It bends to accommodate the straw. And you can literally see that this water is forming this cohesive barrier. And in fact, as I pull the straw up, you'll be able to see the water start to come up with it. There you go, you can just see that happening. And that shows us how strong this force of cohesion within the water molecules is. And in fact, you can also see cohesion in the meniscus because inside a straw. Now this straw is largely see-through, and what you should hopefully be able to see is that there's a meniscus here too, although you can't really see it. There we go. So this is a meniscus inside my straw. You can in fact see the curved shape that my straw has. The water inside the straw has this curved shape. The water curves up the edges of the straw. And this time it's because the water is attracted to the edges of the straw. The edges of the straw have a charge as well. So this is adhesion. So we have the same meniscus, cohesion on a penny, and adhesion inside the straw. And just to show you how different this 2p looks now that we've gotten used to it with this huge meniscus on, that is what it looks like without the water on it. So it's a huge difference. In fact, there's quite a lot of water there. So we're also going to demonstrate adhesion. So that adhesion, or the adhesive property of water molecules, causes the molecules to stick to other substances, okay, that have negative or positive charges. So I'll have a go at giving you some examples of this, some demonstrations. Okay, so we've already looked at cohesion, and whilst we were looking at cohesion, we talked about adhesion, both the adhesion to the straw, inside the straw where there was a meniscus, and we also saw the adhesion between the water and the straw that I poked into the meniscus on the 2p coin. So the first experiment is using an atomizer to spray water droplets to the underside of a horizontal piece of glass. So I have my atomizer, it's just a spray bottle I happen to have in my kitchen, and I have a piece of glass which I've literally taken out of a photo frame, and what I'm going to do is, it does turn into a bit of a mirror. Let's see if this works. So what you can see here, hopefully, you can see how the water has congregated into little drops. Okay, and actually what it's attached to and what it's gravitated to is the little bits of dust and debris on this glass. Solubility. So the polar nature of the water molecule, which means it has a positive and negative end. So the polar nature of the water molecule means that it will be attracted to other molecules that either have a positive or negative charge, or both. So I'm going to add some notes on this. Okay, so polar nature means that it has a positive or negative, or positive and negative end. Okay, so in ionic compounds, which we're going to talk about next, so ionic compounds are made from negative or positive ions that are bonded together. So those compounds can be separated when placed in water. So ionic compounds can be separated when placed in water. That's called being dissolved. And I'm going to demonstrate this with some substances dissolving. Now, I've only got so many substances we can do this with at home, but we will have a go at that. So our final experiments are going to be on the topic of demonstrating solubility. So we're going to add sodium chloride, table salt. Literally, I'm using bog standard table salt from the supermarket. Okay, and as you can see on the ingredients list, okay, it is just listed as salt. It's got some other ingredients in it, but we're not going to worry about those. It's primarily salt. It doesn't give you the scientific name for salt, okay, but salt is sodium chloride, this table salt we're using. So as you can see, I've poured some salt into this glass here. I'm just going to add some water and see if it can dissolve the salt. Now I did this once already and the salt did not dissolve properly because I added far too much salt. Hopefully this time the amount of salt I've put in is considerably less and it will dissolve. And in fact you can tell that it has largely dissolved because you cannot see any white salt crystals at the bottom. It is grey. And just to show you that there is a limit to this solubility, I will add some more salt. And keep stirring. And it's getting more and more difficult to dissolve that. You can see some of the salt is left on the bottom. Okay, and now I can add more and more salt to it. And now there is so much salt in there, it's just not going to dissolve anymore. So there is a limit to how much salt will dissolve in my water. So we're going to do something similar. Now I don't have copper sulfate, that is a chemical we have at school, not something people have at home. Okay, that is I think blue crystal substance. So you're just going to have to coat with with sugar. This is literally just granulated sugar. Okay, and the contents of it, well, it doesn't even have ingredients this because it is quite literally just pure sugar. So I'm going to pour a little bit of sugar into here. Very similar to what you would do with a cup of tea or a hot chocolate or when you make gravy. There are lots of things that require you to dissolve a powder or a solid in whatever form, crystals or powder, into a solvent. Now this time the solvent is water because that is what is dissolving, or that is what the substance is being dissolved into. So the solvent is the water. The solute is the sugar, that's what gets dissolved, and the solution is just sugar water. Now it would probably have helped if I had used icing sugar because it's much smaller in size, doesn't have quite such big granules, or if I'd used hot water like you do in a cup of tea. In fact, this is not working very well. I've got a better plan. So what I'm going to do is, I like a cup of tea, I'm sure many of you do, so just to demonstrate that sugar dissolves easier in a cup of tea, I'm going to put about the same amount of water in, not too much, or tea in fact, it's quite warm tea, it's not hot but warm. I want to make sure there's not so much tea that you can't see to the bottom, that's about right. And I'm going to put in a little bit of sugar there. Now that's quite a lot of sugar there, you can see it at the bottom, you can see the little crystals, yeah? So I'm going to give that a good stir. We'll see if we can't get all that sugar to dissolve. It might take us a little bit, but I think we're mostly there. And there we go. There is no sugar in the bottom of there anymore. So as you can see, all of that sugar has dissolved in the warm tea. Much easier, I might add, than it dissolved into the water. So why does this dissolving occur? Well, in the salt, the positive ions are sodium and the negative ions are chloride, and they are pulled apart from their giant ionic lattice because the positive and negative ions normally are attracted to each other. So they're pulled apart from their lattice by the water molecules because the water molecules are polar and have positive and negative ends. Similar things happen when adding sugar to tea, and there are positive and negative parts in sugar, and they are attracted to the positive and negative parts of the tea, and that breaks up the molecule from its big structure into tiny individual sugar molecules attached to the water in the tea. So now that we've completed the lesson, I'd like you to go and do the knowledge and application check. There are 4 questions here, and then there are an additional several more questions here, so from question 5 all the way to question 11. So I'd like you to pause the video and complete that, please. So we're going to go through that now. Opposite charges attract. Why is water a polar molecule? Well, it's a polar molecule because it has a positive and negative end. Name the type of bonding in a water molecule. That is covalent bonding. State how similar charges interact, or similar charges repel. Give the name of the outward curve found on the surface of water. This is called the meniscus. Pay attention to the spelling. Meniscus. State how opposite charges interact, while opposite charges attract. Name the type of bonding found in copper sulfate. So copper sulfate, as it's easily dissolvable in water, in a solvent, has ionic bonding. And that means that it is made of positive and negatively charged ions, all attached to each other through electrostatic forces. Name the type of bonding in a water molecule. That would be covalent bonding. Not sure why we have this question again. Apologies for that. Question 9. Satellite navigation systems in cars can be stuck to the windscreen using a suction cup. Explain why we wet a suction cup before applying it to the window. So the reason for this is simply that the water is attracted to the glass of the windscreen using adhesive force between the water and another charged surface. Question 10. Some people add sugar to their tea. Explain why we do not see the sugar at the bottom of the cup after the drink is finished. Well, the reason for this is that the sugar is able to dissolve in water. Question 11. Explain why a pond skater is able to sit on the surface of a pond without sinking. The reason for this is due to the meniscus that forms on the water, which is the cohesion or the cohesive force between the water molecules. It forms a strong barrier on the surface of the water, and the pond skater is not heavy enough. It does not have enough mass or weight, in fact, it does not have enough weight to break through that cohesive force between the individual water molecules. Okay, so make sure you've marked those and give yourself a mark out of 11. If you've got less than 5 out of 11, you really need to do this again, have another look through the lesson. If you have got 9 or more, then you've done exceptionally well. Well done.